So we are placing a wire of non-magnetic material, that is iron, cobalt or nickel we are not taking. So this wire is taken and we have to pass current through this wire. To pass current, we require suppose one battery there and rheostat is used. So this is suppose aluminum wire or copper wire maybe. This is placed in north-south direction. In the direction of Earth's magnetic field we have placed. Now, below this wire, a compass needle is placed, or above this wire we are placing a compass needle. So a compass needle is placed below this wire. So we have placed it north-south, so the compass needle will show north-south. So this will be the situation. Now, as you put the switch on, and we start passing the current, we will observe this needle deflects from its original position. Earlier it was showing north-south due to Earth's magnetic field. Now it shows deflection. That means some other field is also created. When we put it off, compass needle again come to the same position, north-south. Whether you are placing compass below or above or sidewise, it shows deflection. That means magnetic field is produced around this wire in all the directions. Above the wire, sidewise, below, in all the directions. When we increase the current by changing the rheostat, it was observed that needle shows more deflection. That means stronger magnetic field is induced here. When we move the needle away from the wire, suppose more below we are keeping, we will observe the deflection is less. That means magnetic field is not uniform everywhere. Very close to the wire, strong magnetic field, but after that strength keep on decreasing as we move away from the wire. Deflection of the needle below the wire and above the wire is opposite, is not same. That means magnetic field induced around the wire is not in same direction, it is in different direction. And afterwards, the direction was given by right hand thumb rule. We are doing in class 10 we have done. What is that? If this is the current carrying conductor, suppose this is we will keep our thumb in the direction of current. So this is the current is flowing from bottom to top. We will keep our thumb like this, and the curl of the finger, that is movement of this finger, will give the direction of magnetic lines of force. So if current is passing this way, magnetic lines of force is anti-clockwise if you see from above. If you see from below, it is clockwise. If the current direction is down like this, clockwise when you see from above. If this wire is placed north-south direction, then what will be? When we are placing like this, it is suppose this is towards south. So it will come like this. It will go towards east. Here up, it will go towards west. So in this case, the deflection of the needle will be this north pole of the needle will show eastward. And when you bring it up, the north pole will deflect towards west. So in this case, when we pass the current, we will observe the needle has come to this place. Okay, maybe like this it has come. So it will deflect towards east. This is suppose east, this is west. So north pole will deflect towards east, south pole will come towards west. Whereas if the needle is placed here, then what will be? Original was this one, but it will deflect in this direction. This is the direction. So it will deflect towards east. So it will deflect towards east, south pole will come towards west. Whereas if the needle is placed here, then what will be? Original was this one, but it will deflect in this direction. It will deflect in this direction. So it will deflect towards east, south pole will come towards west. Whereas if the needle is placed here, then what will be? Original was this one, but it will deflect in this direction. this is north, it will deflect towards west. This south will deflect towards east. This we have done in class 10. Now, what are the conclusions? That also we have done in class 10. So, we are supposed to just recall those conclusions of this experiment. So, one is the magnetic field is induced around the current carrying conductor. Magnetic field is induced conclusions. Okay. Around current carrying conductor. Second is the magnetic field strength or magnetic field intensity is directly proportional to current. So this magnetic field intensity this B is directly proportional to current passed through the conductor. Third is this magnetic field intensity, this B is inversely proportional to square of the distance. So as we move away from the wire, the deflection keep on decreasing. Direction of magnetic field changes when or become reverse when the current is reverse. When we change the direction, this also changes. As well as the position of the point, where you are placing the point. You are above the wire, you are below the wire, you are sidewise. So it will depend on position also. Okay. Or we can say direction of magnetic field depend on direction of current. And fifth conclusion may be direction of magnetic field is different in different directions. Field is not same around the conductor, on the point around the conductor. Okay, so these are the conclusion which we derived from this experiment, Oersted experiment. And Oersted was the first person who proved that there is magnetic field when or due to current. That's why the name is magnetic effect of current. So when current is passed through conductor, magnetic field is induced around it. Now, how the direction of magnetic field is found?
So don't draw the down part, sir.
So direction of magnetic field So one is right hand thumb rule. Another is also there. The Ampere's floating main rule or swimming main rule. So we will prefer by this one only, as we have done in class. And finally, it will come in terms of cross product. That will be the new thing here, and we will use that cross product only. Okay. So this is what we have done in class 10, but we have to know this Oersted experiment is included in this level. Now new thing here will be Biot-Savart law. Biot-Savart law. Or sometimes it is asked Biot-Savart Laplace law. BSL. Three-star scientist, Biot-Savart and Laplace afterwards. Commonly it is Biot-Savart law. So Biot-Savart law. Now, according to this law, we can find the magnitude and direction both. By Oersted experiment, magnitude of magnetic field we can't find. Only it was concluded that okay, magnitude is directly proportional to the current, inversely proportional to the square of the distance. But how much, how it depend, that was not, means proportionally constant was not determined. So here, by this experiment or by this law, we can find magnetic field, magnitude and direction at any point. So suppose we are considering any current carrying conductor, whatever the shape may be of conductor. It may be regular shape, it may be irregular shape, uniform, non-uniform, whatever it is, no problem. So if current I is passed through this conductor, if we consider a small part of this conductor, suppose this length is delta L. Due to this part, if we are interested to find magnetic field at any point, suppose at this point we are interested to find, okay, here what is the magnetic field? Point is P and the magnetic field is delta B, suppose, at a distance R. Then this law, according to this law, it is said the magnetic field is directly proportional to current passing through the conductor, directly proportional to the length of this conductor. Or generally we say it is current element. So this current element we say the product of current and length. So this current element is a vector quantity. Current is scalar quantity, but current element is a vector quantity. And the direction of this current element will be this one only. So this is the direction of current element. Okay. This is the position vector R. So this is the angle between current element and position vector. So this law, according to this law, it is said this delta V is directly proportional to I, or generally we will say this I delta, and that is current element. Sometimes you will find delta V directly proportional to I, delta V is directly proportional to delta L, that is the length of the conductor. Or sometimes you will find it is directly proportional to current element. This current element has got the same, means unit of the pole strength will be same as current element. Here it is ampere meter current element. This delta V is inversely proportional to square of the distance. This directly proportional to I, inversely proportional to R square. This was we have got from Oersted experiment also. New thing, it is included, that is current element, and this delta V is directly proportional to sine theta. This was the new thing given by this one, Biot-Savart law. So if we combine all these, what we'll get? So according to this, what will be? This delta V will be directly proportional to I delta L sine theta over R square. Theta is angle between current element and position vector. If you are taking this side, then this angle. If current is flowing in this direction, current element will be this way. So current element will be along the tangent and in the direction of current flowing. Now, when we remove this velocity constant in magnetic field, in case of magnetic chapter or magnetic field, we are knowing what is the constant. So this delta V will be mu naught over 4 pi or mu by 4 pi, you can say, for any medium. If it is in air, then mu by 4 pi, mu naught by 4 pi. And we have already finished that part. I delta L sine theta over R square, or we can say mu naught mu R. For air, it will be mu naught by 4 pi. For air or for vacuum, this delta V will be mu naught over 4 pi I delta L sine theta over R square. Now we want to express it in terms of cross product. Now according to this right hand thumb rule, what is the direction of magnetic field? If we say this is the thumb, then here we are interested to find, then in this way. So it is inward. So magnetic field due to this will be here, the direction is inward, that is cross. Now how will express this one? Two vectors are there, I delta L and R. So what will be the way I delta L cross R or R cross I delta L, so that we can get inward? Now see, if you are saying I delta L cross R, I delta L cross R, so it is coming this way. No, sir. So I delta L cross R, then only it will come inward. Because it is opening here, so it can't move. So I delta L cross R will be inward. R cross I delta L is outward. But the magnetic field is here inward. So we will write it I delta L cross R. Now R is not here. So we can write it. So this delta V will be mu naught over 4 pi. We are talking about in air or vacuum. So this I delta L, this is the vector quantity, cross unit vector R, we can say R square. Because R is not here. So we can multiply by unit vector. Or sometime we find this is mu naught over 4 pi I delta L cross R vector. Then it will become R cube. As in Coulomb's law also we have seen. Unit vector, this R will be, so this unit vector R is what? The vector R by its magnitude. So this we will frequently use to find magnetic field due to current element. So always we'll use the cross product I delta L cross R, and that will be the direction of magnetic field. Okay, already time up.